Here's your lecture for Integrated 3. It's 11.2.2. How can I graph a 3-variable equation? So now we learned how to graph points in the 3 dimensions, and now we're gonna learn how to graph an equation in 3 dimensions. So it says, in the past, you've used the 2-dimensional Cartesian coordinate system, x and y axes, to graph equations involving 2 variables. In lesson 11.2.1, you used a 3-dimensional coordinate system to plot points. Today, you will use the 3-dimensional coordinate system to graph equations that have 3 variables. As you are working through the lesson, use the following questions to help focus your discussion. How can we use what we know about graphing in 2 dimensions to help us in 3 dimensions? What does a solution to a 3-variable equation represent? Okay, so we're just going to do a little bit. There is an e-tool. It's like a Desmos e-tool, and I'm going to attach it or put a link in Google Classroom that you can click on, and you should be able to get slider bars and see a computer animation of to help you understand more what these planes will look like. But it says consider, so we're just going to do 11.6.3. Consider this equation. I've written it here. Discuss what you think the shape of the graph will be. Well, it's going to be a plane rather than a line. You guys are used to lines, but this one's going to actually be a plane. Letter B says, is the point 4, 5, -2 a solution? So with the little e-tool that I have that you can click on, you'd be able to see, exactly where it is on the graph. But I think that we all know that this is the x, the y, and the z coordinates. So if I plug these in for x, y, and z, it should make the equation true. And then we can check, well, does it? 5 times 4 is 20. 8 times 5 is 40. And 10 times -2 is -20. So those cancel out, and it makes it true. And you can see the answer right there. Your team will be given a list of points. So any points, I'm not going to give you a list of points, but if you did have a list of points to check to see if they are a solution to this equation, you would just go ahead and plug the x, y, and z's in. And you should also know that this, so I've actually graphed this for you, and I'll explain that. Maybe I'll explain that right now. How can you graph one of these? Like, how did I get this graph? Well, what I did is I found the intercepts. So, like, I know that if I want a point on the x-axis, that's when the z, the height, because z goes down here too. When z is equal to 0 and y goes back out this way, those are negative values. Z and y both have to be 0 for a point to be on the x-axis. So if I just pretend that 8 times, if I plug in zeros for y and z, I can just cover them up because they'll just go away. And I have 5 times something equals 40. Well, 5 times 8 equals 40. So I went out to 8. And this, I can call this, since this is on the x-axis, I can say this is 8, 0, 0. This is the x-intercept. This thing is the y-intercept. So the y-intercept happens, remember we have x, y, z. The y-intercept happens when x and z are 0. So you can just go to your equation and turn x and z into 0. I just do it by covering them up with my fingers because that would zero them out. And then I say 8 times something equals 40. Well, 8 times 5 is 40. So this is the y-intercept. Okay, so, and it's 5. And then you can imagine how I found the z-intercept. For x, y, z, I plugged zeros in for x and y, and then I found out what z was. So if I just, zero those out, I could just cover them up, and I could say 10 times something equals 40. Well, 10 times 4 equals 40. Okay, so this is the x-intercept. This is the y-intercept. And this is the z-intercept. And then once I find those, then I just make it like a little triangle. And so this is supposed to look like I have like maybe a triangular sheet of glass or something. And I set it down in the corner, and the three corners, like say this is just, the ground and a wall. And I hope you can understand my picture here. It's like I just took this see-through sheet of glass and leaned it up into the corner. But really, this is just a representation on paper. The plane goes off in all directions through space. So it's kind of like a line, how we show a line on paper and we say, oh, there's our line, but we know that it goes on forever and ever in both directions. This plane goes on forever and ever in all three directions. So there are lots of solutions. There are infinite solutions, like ordered triples. We can call these ordered triples. There are infinite ordered triples that would make this true. This a true equation. I don't know if I want to say too much more about that. You're going to be doing some problems kind of like these ones, and it asks you, like in your homework, it asks you what are the x, y, and z intercepts. So you just do like I just showed you a minute ago, and you just plug in 0 for, like if I want the y-intercept here, plug in 0 for x and z, and I would get 10 for the y-intercept. So that's because x, y, z. So y would be 10. Okay, so just go ahead and try your homework problems, and there's going to be a clickable link in your Google Classroom so you can explore using a graphing tool.